Now we will learn what PLC is doing when no one is looking. We will write our first very simple program. And also I will show you the tools that allow you to look inside of your PLC, inside of your code in real time. Alright, so the PLC is on, but how does it actually work? Let's talk about it for a second. So remember the manual I told you about, the one that you can download from Siemens support page? So I've got this page opened here, but if you want to search for it, I will tell you how I found it. So it's S7-1200 controller. That's what we're searching for. We're only interested in manuals. I want to find the newest one, actually. So I'm looking for this one, and you can download it. I've got it already downloaded. What I want to find is the description, how the PLC actually works. So I will look in PLC concepts, and there it is, execution of the user program. So we have a beautiful description here, how the PLC works, but what I've also found here is this nice picture that has a really good description of how it's working. All right. So what's actually happening inside of the PLC? So we have this graphic here. So this part around here is telling us what's happening at the startup. But for now, let's not get too deep into these details. It's not that relevant at the moment. What is relevant though is this cycle, because this cycle is what PLC is doing constantly. So let's go through it. So first thing that PLC does, it writes the Q memory to the physical outputs. Okay, what is a Q memory? So Q memory is an image of outputs. So what you're going to be doing in the program, you're going to be writing values to the output. You're going to have some logic which will calculate what's going to be set on the output. But PLC doesn't do it immediately. It runs through the entire cycle. It runs through entire OB1, which is a main program. And then after it finishes running through this program, only after that, it's writing this memory to physical outputs. So it's actually setting the right voltage on the output. And next thing it does, it copies the state of physical inputs to I memory. So the concept is very similar. Whatever is on the input, so is it high voltage 24 volts, which means 1, or low voltage 0 volts, which means 0 or false, it makes a snap. And from this moment on, this image is going to be used inside of the program. So the program doesn't use the current state of the input, because this can change during the program running. The cycle is very fast. It can be 2 milliseconds, for example, but still during these 2 milliseconds, the values on the inputs can change. And we want to avoid some hazards because of these changes. And that's why the PLC makes a snap in the beginning of the cycle. And then the next thing that happens, it executes the program in the OB. Right now we're talking only about the OB1. It can be Also in some other OBs, this is a bit more complicated concept. So right now, just remember that most of the program that you're going to be doing, for now at least, is going to be in OB1. So it's going to be the main program. And next thing that happens, the PLC is performing self-test diagnostic, because PLC is actually a very powerful system. It has a lot of self-diagnostic options. So it knows if something is going wrong, it has to know. It has to know because it's controlling critical processes. Sometimes human life depends on the PLC. So it's really important that PLC performs the self-test diagnostics, so it knows that everything is fine with it. And in the meantime, what's happening, wherever PLC is in the cycle, if an interrupt happens, it stops what it's doing, it goes to the interrupt, it performs the program that is in the interrupt, and then after this action is finished, it goes back. And also communications functions, they're also taking place around the clock, so to say. Okay, so they don't have certain time in the cycle of the PLC. They're performed asynchronously. So what's really important to remember, first, it writes the outputs from the image of outputs, that the image was created before in the program. So the outputs are written from this image, then the inputs are snapped from the physical inputs, then the program executes, then we have self-test diagnostics. This is not something you have to program. This is something what PLC does by itself, and then the cycle goes around. So I think this is very important to understand how the PLC works. All right. Next thing I want to tell you about is what is a OB. OB is an organization block, which gives you a clue what it does. So it kind of organizes the program. So this is the place in the program from where all the other functions are called. And you can use many different types of OBs. And if you go to add new block and you want to add a new organization block, you can see all the different types of OBs. I would say startup, cyclic interrupt, and program cycle are the most important. So anyway, for now, you will only or almost only be using the program cycle, because you don't need cycle interrupts yet, and you have to be aware of many things before you start to use them. So for now, let's just stick to OB1. Let me go offline, save the project, and I want to show you something that I like to use personally, because it's very convenient. So I double click on the PLC and I go to the settings, and there's this section here, system and clock memory. So what is it? There are two checkboxes here, and I enable the use of system memory byte and enable the use of clock memory byte. So first, the system memory byte. So what it has, it automatically sets some bits in the memory of the PLC. And what are these bits? First cycle. So I will have a tag in the memory of a PLC that will inform me. This is the first scan of OB1. This information can be sometimes very useful, because sometimes I want to perform some actions only on the start of the PLC. So I have this information. Diagnostic status update. I'm not using this one, to be honest. So if the diagnostic status changes, this bit is set. You can use it maybe. I'm not really using it. Always 1 and always 0. Always true, always false. They're very important, and I'm using them a lot, to be honest. The reason is sometimes you just need to assign a constant 1 or constant 0 value somewhere. So I just take one of these bits and use it in the program. And now, clock memory bits. This is also really nice because very often in your program you will need to have something blinking, or you need some event happening every now and then. And this is where you can use bits from this clock byte. So we have a few frequencies available here: 10 Hertz, 5 Hertz, 2.5 to 1.25, 0.6 to 5 Hertz, and half of Hertz. These are just blinking bits, to be fair, but they can be very useful. So I will show you how to use it in the future. Once we have them, you remember I selected these 2 bytes. So now I go to the PLC tags, and these bits occurred here. So as I told you, PLC tags are names for the areas in the memory. So in this case, first scan is a name for address in the memory M0.1. So in Siemens PLCs, we have a few different types of memory. One of the type of memory is M type. We often call them flags. It's not that relevant actually, but imagine there's a space in memory, and in this space we have to number them somehow. We have to find a certain name. So in this case it's M1.0, which means it's byte 1 and bit 0. In each byte we have bits from 0 to 7. So this is what I want you to remember. There are bytes, and in each byte there is 8 bits starting from 0 to 7, and system byte, as you see here, is memory byte 1. So if you want to specify that it's a byte, then you write NB and the number of the byte. And then there is a clock byte, and clock byte is memory byte 0, and it's MB0. And then inside of the clock byte there are these bits, and this is clock 10 Hertz, and it is called M0.0, which is bit 0 in byte 0. 5 Hertz is bit 1 in byte 0. So this is how it works, and I want to write a very basic program that will show you how more or less it works. So before I do that, I'll tell you a bit about ladder logic, because the program is going to be written in ladder. Ladder is the simplest language ever, I think. So why is it so popular in industry? Pretty much before PLCs, everything was controlled by relay logic. And relay logic, I wouldn't say it was simple, but the drawings had certain form, and this form could be easily understood by electricians. Maybe I'll show you in an example. So I create a contact here. After this contact, a coil. So the contact is going to be connected when always true is 1, and on the output I want, what do I want on the output? Let's say on the output I want Q0.0. And one thing I forgot to tell you about before. Again, let's go to device configuration. So as you remember, this PLC has a set of inputs and outputs. All right, and these inputs and outputs, they need some address as well. Remember I told you about the I and Q memory. So this is the image of inputs and outputs. So they also need to be identified somehow. So they are identified as numbers. So I go to IO addresses here, and start address for the inputs is going to be 0, okay? So the first address is going to be I0.0, and as you see, the end address is going to be 0.7, all right? Same for the outputs. First output address is going to be Q0.0, and the last address is going to be 0.7. Actually, we only have 6 outputs, but in this case, I think it just needs to have an entire byte. So addresses for our inputs and outputs will be starting at 0.0. All right, so I go back to my program and see I've added an address. I've created a coil that will control the output 0.0, and I just typed Q0.0 and it gave the name automatically. The name was created in the tag table. I can go to definition. See, we're back to the tag table. This is where output Q0.0 is. I want to rename it because, well, honestly, I don't like the name tag1 too much. Output 0 is good enough for now. So back to the program, and as you see, always true on the entry, contact output 0 on the output code. This is the simplest program we can write, and yeah, let's see how it behaves. So I'm saving the project and I'm going to make a download to the device. So it's going to compile. I could have make a compilation manually before. I didn't do it, so it's being performed automatically. So it's stopping the PLC, and you have to be careful about it. So you have to be careful not to stop a working line, because this can cost a lot of money, all right? So whenever you do the download, make sure you're not doing anything stupid. So as you see right now, the output 0 is lighting, which means this relay here is right now active. It's the contacts there is closed. So oops, I just broke my PLC. I'm just kidding. It's still alive. All right, so this is what's happening. So now let's try something just a little bit one step more advanced. All right, so what is one step farther from here? I would say let's do something very similar, and you will see that a lot of stuff in TIA portal is just drag and drop. You can just drop and drop things and they'll be working. So it's really nice. So let's say we want to do something else with output 0.1. So Q0.1. I don't want to have it tag 1, so I'm going to the definition again. Normally I would use Control Shift D combination, but I wanted you to see what I'm doing. All right, so all right, and on the input, what do I want on the input? All right, I'll show you a trick. On the left, I have my program, and on the right, I have the tag table. And now what I can do, I can just drag and drop things from here. It's that easy. I split my window and I have my program on the left and I have the default tag table on the right, and I can just drag and drop stuff from one side to the other. I'm saving the project. Maybe let's add something to network 3. I'm using Control and drag and drop to copy things. So it's also very nice. And also one more thing that's really pretty. It's like in Excel. So you can just drag things like in Excel and see the next address is Q.02, and here we have output 2, so it's even incrementing the numbers. So here I don't want to use output 1 because, guys, remember, when it's about the outputs, you only want to write it once. In general, I strongly advise you to only write memory, whatever it is, in one place. Sometimes there can be exceptions to this, but I would say 99.9% of the time you only want to write things in one place. All right, let's add another call here, and let's make it clock and see. Look, it's helping you when you're trying to write something. Let's make this one much faster. I don't want to make it too fast, so let's make it 2 Hz. And now save the project and download, and let's see what happens. All right. All right, so 0 is always true. Output 1 is blinking at 1 Hertz, and output 2 is switching at 2 Hertz. Yeah, it's almost like music. I remember I went to a club in Belgrade once, and and the music was like this. So yeah, that's fun, right? All right, I'm a bit tired with this music. I've had enough, so I'm going to online and diagnostics. And look, this window opens also on the side, so the window is now divided. If I want to make it like it was, I'm clicking here. The window is not split anymore, and back here. All right, so I go online. And what I want to do, I want to stop the PLC because it's annoying me. Yes, all right. So I've shown you how it works with a real PLC. Now let's see how it's going to work with the simulator. So what I'm going to do, I'm going to go offline with this PLC. I'm going to switch the simulation on, right? So I'm going to make a download to a simulator. I'm going to switch the PLC to run. The PLC is running, at least it seems like it's running, but we don't hear any ticking, right? Because obviously we don't have a PLC that would make this sound. How can we see if it all works properly? So first thing you can do, and this is something you're going to use a lot, we can go to the program and click this button here, monitoring on off. All right, and you're going to see in real time what's going on inside of the PLC. Okay, what's going on in the program. So we see it's switching here exactly like it was with a real PLC, but it's being done by the simulation. So this is one way you can do it. So watching these outputs in the program. Another thing you can do, you can create a watch and force table. Actually, we're not going to use a force table right now. We're just going to use a watch table. So we created a new one by double clicking at add new watch table. And what do we want to watch? We have to put an address here. All right, so let's have a quick look again what address we're using. And we're using Q0.0, Q0.1, and Q0.2. So I'm just going to type it here, and it automatically put the name here and display format. So what I'm going to do next, I'm just going to drag and I'm going to add some more values that I can watch. I think I need one more to watch the entire byte. All right. And also same button, and now I'm monitoring the output. I don't have the lights on the PLC, but I can watch the outputs here. So these are the two basic ways that you can monitor what's happening inside of the PLC, even if you don't see the real output. So in the next video, I will show you how the ladder actually works, why it works like this, and also we will try to make a first simple program simulating it in the factory I/O, and this will give you much better understanding of how this PLC control works. So that's it for now, and see you in the next video. And please remember, if you haven't done it yet, join the Facebook group.